Last but not least, part 3 of the Intro to Astronomy Notes. Flip class. We left off with this practice question. However, as I went back and listened to it, realized this part did not video record well, or did not record. So the practice question, you're going to practice in your seat, and I want to see this, and we'll work on it in class. Hopefully before you get to this, but you might be awesome and do it before, which I'll give you something similar to it. So if you're 9 times 10 to the 7th kilometers away in space, and when the moon is at apogee, it's too far away from us, and the umbra does not hit Earth, so we get an annular or a ring eclipse. We don't get the whole thing. So you don't get a partial eclipse, like you see in the picture in the background, or an annular or ring eclipse if it's perfectly lined up. You can still see the sun around, like a ring around the entire sun. So it's obvious that picture taken from the same place on Earth, the moon does look a little bit smaller at apogee because it's a little bit further away. It's 405,000 kilometers away, almost 406,000 kilometers away, where at perigee, it comes clear into 357,000 kilometers closer. The ironic thing is, we don't really notice the size difference a whole lot, especially when it's high up in the sky. But when it's low on the horizon, you have something to compare it to, like the stuff on the horizon, the trees and the skyline. That makes it look a whole lot bigger. So warm up you guys are going to do at your seat. If you want to do it here for practice, go for it. Look at the noctilucent clouds up there. So Zach and Richard in a spaceship approaching Mars at 1.52 AUs away. Remember, an AU is the average distance of the Earth from the Sun. They send a radio message traveling the speed of light that it's lunchtime, high noon. If your clocks are synchronized, what time does their message reach you here on Earth? So we've got to take the 1.52 AUs times our 150 million kilometers per AU. That'll convert to kilometers right away. We want to convert to kilometers because the speed of light is in kilometers per second. So take our 228 million kilometers from Earth to Mars, divided by the speed of light, gives us 760 seconds. Okay, we're getting there, but we're not there yet. 760 seconds divided by 60 seconds per minute. Now we get 12.67 minutes. Getting there, still getting there. If you do math the long way, you come up with 12 minutes and 40 seconds. If you do it on a calculator, you get 12.67. So we take our 0.67, 67% of 60 seconds per minute, 0.67 times 60 seconds, or 2/3 of 60 is 40 seconds. So you get property 12 minutes and 40 seconds. So the time it would reach Earth, if it were high noon when he released it, would be 12, that's noon, 12:12, so 12 minutes after 12 and 40 seconds. So the answer down there would probably be, the actual answer for the question would be 12:12 p.m. and 40 seconds. So that's noon, 12 minutes and 40 seconds after noon. If Brian visits Neptune, and he's way out there, 30 AUs away from the sun, and we happen to be on the same side of the sun as Neptune in syzygy, so we're perfectly lined up, how long would it take for radio signal to reach Earth? We add an extra twist on here. We know he's 30 AUs from the sun, but the Earth is 1 AU from the sun. On the same side, you're going to take 30 minus the 1 AU, so we are 29.1 AUs from Neptune. Bam. 29.1 AUs away. You take your 29.1 AUs times 150 million kilometers, roughly, per AU, gives us 4,365,000,000 kilometers away. Now you take those kilometers, divide them by the speed of light, or speed of radar. (242.5 minutes). Ooh, that's easy, because a half minute is 30 seconds, so put that in the bank. A green number there, just put 30 seconds in the bank. Take 242 minutes divided by 60 seconds. 242 minutes divided by 60 seconds is 4.0333 hours. And I picked a great place to do this in the front porch, and someone loud is coming down the street. 0.333 hours times 60 minutes per hour is exactly 2 minutes. That gives us exactly 2 minutes, 30 seconds. 4 hours, 2 minutes, 30 seconds for a radio signal, or light for that matter, to reach Brian at Neptune. So the light bouncing off Neptune, if we could see it with our naked eye, takes 4 hours just to get here. It takes over 4 hours for sun's light to get from the sun to Neptune. It's pretty far away. And with that, we end the notes. Study for your test, and that's all, folks.